As we continue to talk about logarithms, we now consider logarithmic functions and graphs. Of course, we've seen some of these graphs, especially as compared with exponential functions. So here we're looking at how to interpret vertical asymptotes, how to find intercepts, how to apply transformations like shifts, stretches, and reflections, and of course, explain the inverse relationship between logarithmic and exponential functions. I mean, I've talked about this a couple of times. That's the connection between the inverse relationship between logarithms and exponents. So first off, we consider definition of logarithmic function. Of course, we've been doing that in every video on logarithms. So a logarithmic function has the form y equals log x to base a, and that base a must be greater than 0. It has to be positive. Then a has to be not equal to 1. So in summary, we can say a should be greater than or equal to, no, a should be greater than 1 in short. So a greater than 1 combines these first two conditions. Then the other thing is that this x can never be negative, all right? Because if you raise if no exponent gives you a negative value, in short, that's the idea. So x is always positive now. So the logarithm answers the question, to what power must a be raised to obtain y? Okay, I mean to obtain x rather. So equivalent exponential form of this expression now is that a carries y on its head. So we have y equals log x to base a, and that means a carries y on its head, and that is equal to x. So it means a must be raised to power y to get x, like that. So we go for the next thing, which is the graph of y equals log x to base a. That is when a is greater than 1. For instance, you have y equals log x to base 2. So the key properties for this now is that the domain is from 0 to infinity. Okay? The domain, that's the possible values of x will lie between 0 and infinity. And then the range, that is the values of y, will be from negative infinity to positive infinity. All right. Then vertical asymptotes is x equals 0, and the x-intercept, just like we saw before, is y comma 0, and then there's no y-intercept. So we see that as x approaches positive 0 on the positive side, x approaches negative infinity. As x approaches infinity, log x to base a approaches log x to base a approaches negative infinity, it approaches positive infinity. Well, instead of just telling stories, let's look at it on Desmos. This is talking about log x to base 2 now. Okay, log x to base 2. So we have log x base 2 base 2. So see this now. So that's what we've been saying. This is the intercept 1 comma 0, as we have it here. So the domain of the function itself is 0 to infinity. So you see this line doesn't cross to the negative side. That's why it is from 0 to, and then you see it keeps going endlessly on the positive infinity side. So the possible values of x is from 0 to infinity, but the range itself is from minus infinity to infinity. So the possible values of y, that is from minus infinity to infinity. So on the vertical axis now, it's coming from negative infinity, and this and here now it keeps rising, you know. Uh it keeps rising. So if I keep shrinking it, so you can see it keeps going up and up and up and up like that. So let's come back home, right? So the range is from minus infinity to infinity. Then the vertical asymptote is x equals 0. So that's x equals 0. X equals 0 is the vertical asymptote, as you can see. So the y is trying to come to 0, but it's never getting there, right? So see that x equals 0. So that's the vertical asymptote, x equals 0. Then another thing is that there's no y-intercept. As you can see, the graph doesn't cross the y-axis anywhere. Then as x approaches 0, then the function approaches minus infinity. So as you can see here, as we come closer and closer to 0, this function keeps moving towards the negative axis, like that, negative y-axis. So then as x approaches infinity, the function also approaches infinity, and that's what we have here. So as x keeps going, you see that this the function keeps growing too. Okay, the function keeps growing. So as you increase the values of x like this, so the function keeps growing and growing, and it's not ending, it just keeps going on like that, right? So that's the meaning of that. Then let's go ahead and talk about some sketching. So imagine you want to sketch um log log 3, log x base 3. Okay, log x base 3. Sketch y equals log x base 3. So first of all, you want to generate key points. So we already know that log 1 base 3 is 0, log 3 base 3 is 1, log 9 base 3 is 2. We know all these ideas, right? So, and then we also know that log 1 over 3 base 3 is minus 1. So we have these are y values now corresponding to all these possibilities. So when x that means that when x is 1, y is 0. When x is 3, y is 1. When x is 2, y is 9. When x is minus 1, sorry, when x is 1 over 3, y is minus 3. Then we can in step 2 now we can then plot the points. So we can plot 1 0, these are values of x now: 1 3 9 1 over 3, 1 0 3 1 9 2 1 1 over 3 minus 1. Then draw a smooth uh increasing curve that approaches but never touches x equals 0. Well, I mean, Desmos makes that easy for us. We just have log x to base 3 here, and that's it. So as you can see, when x is 0, y is 1. When x is 3, somewhere around here. When x is 3, somewhere here. When x is 3, y is... Okay, what are the other points now? So 103192. Okay, 103192. So we have 3 here. 3, 3, 1. Then we have 9 2. Should be 9 2 somewhere here. This is 9 2. And so on and so forth, right? So, but Desmos has uh, nicely drawn this for us. Okay. So, yeah, we can do that. So next, what if we want to graph when the base lies between 0 and 1? So when y is equal to log half x, the properties now, okay, I mean, again, I think I can just do that. Log x to base half, so to base 1 divided by 2. Okay, see what happens here now. So now it's like it's a flip over of log x to base 2. So in this case now, look at what happens. So the domain again is still 0 to infinity, same thing. All right. Then the other thing now is that the range is still minus infinity to infinity, right? Because it's coming from, so this angle one is now going to the negative side and it keeps going, and this one is going to the opposite, the positive side of y. This is always going to the negative side of y. So that's why we have the range to be minus infinity to infinity. And the vertical asymptote is x equals 1 as usual. So you see this line, x equals 1. So because this one is moving towards x equals 1 and it never gets there, then the intercept again is still 1 comma 0. This is the same 1 comma 0. So I mean, to compare that, right, we just have log x to base 2. Log x to base 2. So you see it's the same 1 comma 0 as the intercept. So like this. uh then the graph is decreasing in this case. As x goes towards positive infinity, the function goes to infinity too. So as x approaches 0 from the positive side, so the function grows towards infinity. Then as x goes towards infinity, log x goes towards negative infinity. So as x keeps increasing, you see this the function keeps moving towards negative infinity like this. So this is it moving towards negative infinity as x goes towards infinity. So we have that. Then we can talk about intercepts of logarithmic functions. So to finding the x-intercept of a logarithmic function, the intercept is where it cuts the x-axis. So what you just need to do here is to set y to be equal to 0. So the x-intercept is where y is 0. So in that case now, to find the intercept of a logarithmic function, so instead of having y equals log x to base a, y is 0 in that case. So you have 0 equals log x to base a. And by the time you say make a raised by 0, x now is equal to 1. Therefore, every basic logarithm function passes through 1 comma 0. Any logarithm function you have at all will always pass through that point because it is true for every function that any base raised power 0 will always give you 1. So the x-intercept of any logarithm function is actually 1 comma 0. Okay. Now we have a question. Does the log function have a y-intercept? Hardly. So if you set x to 0 now, you see, if you set x to 0, we have y equals log a to base 0, log 0 to base a, which is undefined because the basic rule of logarithm is that this value here must be positive. It cannot afford, it can't be 0 and it can't be it must be positive, that's all. It must be greater than 0 in short. So this is undefined. So therefore, logarithmic functions have no y-intercept. So every logarithmic function has an x-intercept at 1 comma 0, but every no logarithmic function has a y-intercept. Instead, they have a vertical asymptote at x equals 0. Okay. Then we have transformations we may want to talk about. Transformations of logarithmic functions. So we have the general form of a logarithm function is this: y equals a log a x minus h plus k. So effect of transformations now, x minus h here shifts right h, x plus h shifts left, then plus k. This plus k shifts up, minus k shifts down. A is greater than 1 is a vertical stretch. If a is between 0 and 1, it's a vertical compression. And a less than 0 is a reflection across x-axis. So, I mean, it's uh, almost true. It's about true for regular polynomial functions. So imagine this example now. Y is log to base 2 of x minus 3 plus 2. To determine asymptotes, of course, the asymptotes. So to determine asymptote, we set inside equal to 0. So just set x minus 3 to 0. So x minus 3 equals 0. So that means the asymptote is x equals 3. So the vertical asymptote is x equals 3 in that case. So to determine the asymptote, we just set the inside to 0 because you need log 0 here, right? Which is undefined usually. Then you can also transform the key point. So the original point, right? Uh, when x is 1, all right? So at 1 equals So original point, if you set y to be 0, okay, you have 1 comma 0 here. Then because to every log passes through this, then shift right 3, you have 4 comma 0, and then shift up 2, you have 4 comma 2. Okay, let me just plot that so we can see what's happening. Log x minus 3 to base 2 plus 2. Log x minus 3. So we have log x minus 3 base 2 plus 2. Okay. So we see the asymptote is x equals 3, as you can see. X is equal to 3. So that's the asymptote. That's where it's going towards it, but it doesn't ever get there. So let's see what happens. So what if we have if I say 3, if I put 3 here, so you see it stretches it up, by that factor. What if I say 1 divided by 3? The 1 divided by 3, okay, 1 divided by 3. Okay, it's compresses it a bit. Then what if I shift this now, make this 4? You see this one, so this one moves away. What if I move it? This now becomes positive. So let's see what happens. So it shifts to this side now. So let's go back to x minus 3, x minus 3. Okay, we are home now. So what does this 2 do? So if you make this 2 3, what happens? So see what it was before. 3. So 4 now. It crosses that 4. Then what if I make it minus 4? So it comes back down here. So we have 4 comma 0 now. In fact, minus 4 comma 4 and all that. So that's how all of that goes. So in example 3 now, imagine minus 2 log x base 3. So the effect of this is that there's a reflection across x-axis. So minus 2 log x to base 3, okay, minus 2 log x base 3. So it now reflects across, you have reflection across the x-axis. Then what else? vertical stretch by a factor of 2. Okay, you have a vertical stretch by a factor of 2. If the 2 wasn't there, it compresses. So but by adding the 2 now, it stretches to 4. So then what else? Um, Asymptote remains x equals 0, then domain remains 0, infinity, and range remains minus infinity to infinity. So that's what all of that shows. Then we go on. Talking about inverse relationship with exponential functions, I remember when I taught under calculus, I talked about functions, graphs of functions, and all of that. So imagine that we have this. Let's even use the general exponential function. The natural function, you have y equals e raised power x. Imagine you have y equals e raised power x. So the inverse, to find the inverse, okay, what do? We have, okay, I think we even start with f of x. So f of x equals e raised power x, right? I want to find the inverse. So we now say we have f of x equals e raised power x. So we then say let y be equal to e raised power x. The deal here is to make x the subject of formula, okay? And that's the foundation. So, and the only way to do that is to take the log of both sides. So I'll take the natural log of both sides. Ln y equals ln e raised power x. By the way, we know that this is ln y. So ln y is actually log y to base e, I mean clearly, and this is also log e to base e raised to power x. So that means we have, okay, let me make this tidier. So I have log y to base e equals log e raised to power x to base e. Okay, so we have log y to base e on the left hand side. On the left, we have the power law that x can come down. We have log e to base e. So the log of a number to its the same base is always equal to 1. So log y to base e is equal to x here now, because this whole thing is 1. So that's x times 1. So that's x. Okay. So from there, what do we have then? Log y to base e is equal to x. So we have isolated x. So we see that x now is log y to base e. So we can then say that if we now do all the transformations, we can now say f of x is equal to log you know you want to you can now transform. You can now transform it. Now you just have y equals log x to base e. Okay, which is ln x in short, which is this is equal to ln x. So we can conclude, so the inverse of y equals e raised power x is y equals ln x. So that's established that the inverse of exponent is logarithm, basically. So that's what all of that story on the notes is going to be about. So logarithmic and exponential functions are inverses. So y is 2 raised power x and y is log x to base 2. They are reflections of each other across the line. I think we did that in the previous video. So or let me even do e raised power x and ln x that I did. So it's basically the same idea. So we have e raised to power x like this, and then we then have ln x. So, and then they are reflected about x equals y. So, this is like their middle points or something like that. Okay. So across they are reflections of each other across the line, and that's why they are inverses. Okay, I mean, verifying algebraically, you can start with y equals 2x and then you swap x equals y, x and y. So x is equal to 2 raised by y. So solve for y now. So y is log x to base 2. That's the kind of thing I did for natural logarithm on this other on the worksheet. Thus, logarithmic and exponential functions are inverses. That is that is clear. Okay. So comparison table now, we see for exponential function, y is equal to a raised by x, and the domain is x values can range from minus infinity to infinity, but y value ranges from 0 to infinity. So, and the horizontal asymptote is y equals 0. Whereas for logarithmic function now, you have y equals log x to base a. So you see, there's a flip because they are inverses of themselves. The domain here, the domain for exponents becomes the range for logarithms, and the range for exponents becomes the domain for logarithms. And then the horizontal asymptote here is y equals 0 for exponents. But for logarithms, the vertical, you have a vertical asymptote x equals 0. So you can see that they are actually inverses of themselves. So we have example 4 now. So you have f of x is 3 log to base 2 of x minus 1 minus 4. So the domain, of course, for the domain, we get x minus 1 greater than 0. So we have x greater than 1. So in this case, now the domain is 1 to infinity based on what we have. Because if you have less than, if you have 1 even, it has to be greater than 1. Because if you have 1 here, this will be undefined. So x has got to be greater than 1 for this to even hold. So the domain is from 1 to infinity, as we find here. And the vertical asymptote, you equate x minus 1 to be 0, and then you get 1. That's the vertical asymptote for this. And then the range is minus infinity to infinity, whereas the x, we have to get the x-intercept, you equate y to 0. So it sets this to 0. You have 4 here. You have 4 over 3. Then log to base 2. So you have 2 raised by 4 over 3, x minus 1. So the exponential form is now x equals 2 raised by 4 over 3 plus 1. So this is the x-intercept in that case. Okay, we want to plot that just to see. So we have 3 log to base 2 of x minus 1 minus 4. Okay, 3 log 3 log to base 2 of x minus 1 minus 4. Okay, so all those things actually hold that of course we see that the domain is from 1 to infinity, clearly so. uh So you see, because the asymptote is even at 1, so it's coming towards 1 and it's never getting there. If you look at this line now, it's coming towards 1 but never getting there. Then you have all these things listed there. Again, the vertical asymptote, of course, is x equals 1. Like I was saying, just say x is equal to 1. So you see, it's always trying to go towards the 1, but it's hardly ever getting there. Then you have the range is for minus infinity to infinity. That's the x values now. So the x values are from minus infinity to, no, the range is the y values, right? The y value is from minus infinity to infinity, but the domain is from 1 to infinity. We've taken care of that already. Then the x-intercept is 2 raised to power 4 over 3 plus 1, okay? X is equal to 2 raised to power 2 raised to power 4 over 3, 4 divided by 3, okay, inside is a plus 1. So you see that's the x-intercept. Yeah, that's the x. Is that really the x-intercept? Okay, I think something is not right here. 4 over 3 plus 1. Oh, okay. My fault. So it is this now plus 1. Yeah. Okay, now it makes sense. This is it right here. That's the x-intercept right there. Then yeah, we have all of that. Finally, we have the practice problems. So we have different segments. Basic properties: state the domain, range, vertical asymptote, and intercept of y equals log x to base 2. I mean, we know all these ones. So then sketching and key points. You want to sketch this. I mean, we can easily plot them, like we've seen some examples of that. Then for transformations, now state the transformations for y equals log 2x minus 5. Stage transformations. So, I mean, we discussed about all this a lot. Then solving logarithmic equations, of course, we can take care of all of this. So to solve this, you just have x is 3 raised to power 2, x is 9. So to solve this, we have 5 raised to power 3, that's 125. So x minus 1 equals 125, that's x is equal to 126, and so on and so forth. So here you have log to base 4 of x plus 3 minus 1 equals 0. So just take the 1 to the other side. So you have 4 raised to power 1. So x plus 3 is equal to 4. So x is equal to 1, like that. Then you have this, show that y equals log x to base 5 is the inverse of y equals 5x by swapping x and y and solving. Yeah, we did that already. So with this, of course, there are other things I like to pay attention to again, right? So if I'm going to generate, maybe try to summarize the laws, right? Uh, log laws. Let me just say log laws fast. That's laws of logarithm. So we saw the fact that the log. So I'll just take, let's take natural log now. You can take the common log, log to base 10 or natural log, anyone. So the lane of x plus y, you know, or maybe I should pick a particular base. So let's say log to base a of x times y is always equal to log x to base a plus log y to base a. We had that. That's the product law. Then we have the quotient law that log to base a of x over y is equal to log x to base a minus log y to base a. Okay. Three, we know that the log to base a of x raised power n is always equal to n log, the power comes down, n log x to base a. Now, other ones we're silent about is the fact that the log, okay, well, I made mention of them too, right? So it is because of this one I'm actually trying to do this listing. So if you have log 1 to base a, in fact, log 1 to any base at all is equal to 0 because, of course, a raised by 0 is always 1. So that's very important. 5, we know that log a to base a is equal to 1 because a raised by 1 is always a. Okay? That's another very important one. So what happens if you have maybe log x to base 1 over a? What can we do with this? All right. So these are some very key issues now. So you have log x to base 1 over a. So what what should happen with this? Now let's do a quick thing. So can we just say let x, let log x to base 1 over a be equal to b. Okay, so we're looking for b in short. So that means x is equal to 1 over a raised power b. So that means that we have x to be equal to a inverse a raised power minus 1b. So x is equal to a raised power minus b. So what do? We can take log of both sides. So we have log x equals log a raised power minus b. So that means log x is equal to is equal to minus b log a, right? So again, we are looking for b. So that means that minus b is equal to log x over log a. And if you have log x over log a, that means, okay, of course, we can take the minus away. So b is minus log x all over log a. And we already know that this is the same thing as b equals minus log x to base a. Okay? So you see that this 1 over a introduces a negative into negativity into the whole mix. So in essence, we are saying that this is the same thing. All right, this is the same thing as minus log x to base a. Okay, that's all that is about. So So we're simply saying that log x to base 1 over a is the same thing as minus log x to base a. So this fractional base introduces negativity into this place. So what then happens if you have 7, that's log x to base, say, a raised power n? What do you have in that case? Again, we go on the same kind of journey where we now have okay, you say let this be b, right? So we say let x, or better still, let log base a raised power n be equal to b. So that means we have a raised power n raised power b is equal to x. Okay, so and then we have a raised power bn equals x. Mind you, we are looking for b now. Okay, so we then take log of both sides. So we can say, let's take, yeah, we can take log of both sides, of course. So that's log a bn equals log x, and then that is bn log a equals log x. And we are looking for b, right? So b now is equal to log x all over, okay, let's just leave this bn alone. Bn is now log x over log a. Okay, that means that n itself, actually, or bn for now is still log x to base a. We know that much from previous videos. So b now is equal to 1 over n log x to base a. Okay, so it means that when you have a base that is a power, then so it introduces the inverse of the power, multiplies the regular thing. So we have 1 over n log x to base a. Okay, those are some other possibilities. So 1 over n log x to base a. So here now we have 1 over n log x to base a. So, I mean, for these new things now, of course, we know that log 1 to base 7 is equal to 0, straight up, because it is log 1. Whatever the base is, doesn't matter. So we know log 7 base 7 is equal to 1, straight up. Therefore, this now, we know that log 1 over 7 base 7 is equal to minus, is equal to it will be equal to minus log 7 base 7, which is equal to minus 1, like this. Then when we come here and we have, say, log 7 raised to power 3 base 7, that will simply be 1 over 3 log 7 base 7, which is 1 over 3, simply. Okay, so yeah, I just thought I should introduce those ideas so you can always use them whenever you see them. Though we emphasized these first three, but then there are other things like this that can make you really handle log very well. Okay, so these are some of the log laws. So with this, I come to the very end of this video talking about um logarithmic functions, like that, logarithmic functions and graphs. Let me know how helpful this is for you, and if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you so much for doing that, and if you have not, what are you waiting for? Go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. All right, having done that, you can also become a member of the channel. That gives you some special privileges, like getting to see some videos first, or being the only one to see some videos as a member. And of course, we can also hang out to discuss whatever interests you on my channel. We can hang out online or physically to talk about some of these things, if you are such a member. All right. You can also get PDF copies of some of my notes, based on your request. Um, more importantly, Most importantly, rather, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.